Hello, this is Neela. I'm here on behalf of Space India. And today is World Space Week. It's a special day, not just a special day, it's a special week. From October 4th to October 10th, we have World Space Week. And today, to join us on this special day, we have Dr. Henry Throop, planetary scientist, and I'll introduce him in a bit. Welcome here today, Henry.
Thank you. Hello, welcome.
And we also have Mr. C.B. Devgan here, who's president of Space Foundation and also the coordinator for World Space Week, India. So welcome here, CB. We are happy to have you here today.
Thank you.
Okay. So to start off, CB, would you tell us a little bit more about what is World Space Week?
Yeah, I mean, as the name itself shows, it's a week from 4th to 10th of October, but these two dates are very special dates because on the 4th of October in 1957, Russia at that time sent the first man-made object into the space called Sputnik. And on 10th of October, I guess in 1960 or something, UN made a resolution for all the countries in this world to have a peaceful purpose of space. It is not that if I land on the moon first, then I can claim that satellite as my own satellite, or if I go to other planet and I claim this is my thing over there. So to have a common countries to have which is beyond the Earth, it will be used for only for peaceful purposes, and that 10th of October and 10th you have one whole week. So in around 99 or something, United Nations decided to have this as the World Space Week celebration, in which across the globe we would have the celebrations in astronomy and in astronautics and anything to do with the space sciences. So each and every country celebrate in their own manner, and I mean, they either do competitions, they do film shows, they do debates and things like that, just to make people more interested in the field of astronomy and space sciences. So World Space Week is celebrated in October, from October 4th to 10th of October.
Yeah, thank you for that, CB. And I would like to introduce C.B. Devgan. He's currently the president of Space Foundation, which is a wing of space. And he's committed to spreading astronomy to the masses. He's an amateur astronomer with more than 25 years of experience in observational astronomy, telescope making, and astrophotography. And he's been with space for a long time. And we are happy to have him here on the session with us today.
Thank you.
And now I would like to introduce Dr. Henry Throop. He's a senior scientist in the Planetary Science Institute in Tucson, Arizona, and currently living in Mumbai, India, which is lucky for us. And he received his Ph.D. in planetary science from University of Colorado in 2000. His work focuses on the outer solar system, and he has published over 40 articles in scientific journals on topics from rings of Saturn and Jupiter to planet and star formation to astrobiology and the origin of life. He's a frequent consultant to the US's NASA and National Science Foundation. While working at NASA, he managed 2 major scientific programs, and he's a member of the science team for NASA's New Horizons mission and was involved in the historic flyby of Pluto in 2015. He's also worked extensively with rural schools, helping to develop the science programs and inspire the next generation. He has presented more than 100 lectures for science festivals, planetariums, and schools. His work has been featured in Science, Nature, Time, Washington Post. His work has won him broad accolades. In 2017, he was awarded the US State Department's Avis Boland Award and the American Astronomical Society's Carl Sagan Medal for his work in science communication. We're so lucky to have you here with us today, And today, you're going to be talking about astrobiology with us, which is, in fact, for World Space Week 2017, that is the theme, exploring new worlds. So that's fantastic. And I welcome you to go ahead and present your talk.
Awesome. Well, it's so nice to be here. Thank you so much. Let me start my presentation here. Can you see it on the screen?
Clearly.
Okay. So I'm going to talk about are we alone in the universe and how that relates to astrobiology. When people find out that I'm an astronomer, they often ask me how often I go into space. I'm not wearing a spacesuit right now. This is sometimes I wear a suit, but what I do is I study the planets. I use telescopes and spacecraft, and I don't actually go into space. Most astronomers don't go into space. Most astronomers stay on the ground and use telescopes and spacecraft to study the planets and the stars. And just what we do, I spend a lot of time programming, a lot of time working with computers, a lot of time analyzing data, a lot of time emailing and on phone calls and reading papers and writing papers. These are the sorts of things that I do. And so it requires studying, knowing science, but also knowing how to communicate, knowing how to read, knowing how to write, knowing how to organize projects and so forth. I do get to use some big telescopes. Here's one of the large telescopes in South Africa, which I was able to use. People ask me how I become an astronomer and how you can become astronomers as well. And so I did my secondary education in the US, took lots of math, lots of science. I did a BSc in physics, which in the US is a 4-year program for the BSc. And then I did an MSc and a PhD in astronomy. And you add that up, that's 4 years plus 2 plus 3, that's 9 years of education. That seems like a lot, but the real thing is it was really fun because I got to be an astronomer for 5 of those years while I was doing my postgraduate work. And I got to work with telescopes and work with data and work with other astronomers and present at conferences and really study things in the solar system for most of that time. Now, there's many people from the US who go to school in the US, but there's many people from other countries as well. I was lucky to have many students from other countries who I was working with. And many students from India go to the US or go to Europe to study their pursuits abroad as well. Now, then, after learning that I'm an astronomer, people also ask me, do I think that aliens exist? And well, the simple answer is that if you look at the number of stars in our galaxy, we have about 100 billion stars in our galaxy. That's the one with 11 zeros after it. And then there's about 100 billion galaxies in the universe. And if you multiply those two numbers together, that's 10 to the 22 stars, 22 zeros after that 10. 100 billion stars in our galaxy. And so I think that at least one of those other stars, and probably far more, so many stars out there, it would be strange if none of those stars had planets going around them. However, have we ever found any aliens? And by aliens, I don't mean like necessarily, little green people with antennas sticking out. What we picture as aliens. But what I mean is any sort of life in the universe. Have we ever found any signs of life on any other planet or any other star, anything like that? And the answer is no. As much as we have tried, we have never found any life anywhere outside of the Earth. We've never found anything living on Mars. We've never found any bacteria on asteroids. We've never found any radio signals that have been confirmed. Nothing at all. And so how do we put those together? Well, I'm going to talk about that. And so really, if you step back, one of the big questions that astronomers are asking, or the biggest questions anybody can ask is, are we alone? Is our solar system unique? Is the Earth unique? And is life on Earth unique? And for a long time, we didn't know the answers to those questions. If we step back in time, we go back to the 1500s, we used to think that Earth was the center of the whole universe, and the sun and the moon and the planets went around it. And so here's a picture of where we thought the Earth was at the center of the universe there. And we thought, of course, we're special because it's only us here. And then after astronomers from Europe, Copernicus and Kepler, looked at the motions of planets, they concluded that, well, maybe that the Earth isn't the center of the universe, but the sun is the center of the universe. And so we are just in one of these blue dots out here, one of the small planets orbiting the sun. And so it makes it a little bit less special. We're just one of the planets. We're not the center of the universe anymore. And then in 1700s, astronomer Christiaan Huygens looked out at the stars and said, you know what, all of those stars, and all he could see is they were just little points of light. But he came up with the idea that all those points of light that are so far away and so faint, maybe those are other suns. And he proposed that, and if there are other suns, then maybe each of those stars out there might have a planet going around it, much like ours. And he was the first one to come up with that idea in the 1700s. Now that's a great idea, but it did mean that when he did that, he made us feel less special, because it could be that all of these sources of life could be all over the universe. Now that lasted for a while until the 1930s with this astronomer named Edwin Hubble, and he looked up and he saw, through his telescope, he saw these pictures of what he then called galaxies. And these galaxies are these spiral-armed things, and you can see the spiral in some of these things. This is a picture taken with the Hubble Space Telescope. And you look at that and you might think those are all stars, but nope, all those things are galaxies, all those red and blue things. And what you're seeing there is each galaxy has 100 billion stars in it. And so Edwin Hubble realized that each of these might be the same as the Milky Way. And so instead of us being just one galaxy in the whole universe, there's billions and billions of galaxies in the whole universe. And so we become less and less special with time. Now, since then, in the 1990s and the 2000s, astronomers started to find planets around other stars as well. And so not only are we not the only stars out there, but we might not be the only planets out there as well. We found thousands of planets around other stars all across the universe. And so, as it turns out, we occupy just this tiny, insignificant corner of the universe. And where we live is not particularly special or unique. There's billions of other places just like ours. There's billions of other planets around billions of other stars in our galaxy. And many of them may be similar to our own. And so now we can answer these questions. Is the solar system unique? No, it's probably not. There's probably billions of other places that look like our solar system. Is the Earth unique? Probably not. The Earth is special. We live here. But there are probably billions of other Earths all around the universe as well. And is life on Earth unique? We can't answer that question yet, and that's what we're going to try to do. So if we're trying to search for life throughout the universe, we can't search everywhere because the universe is so big. You know, we can't search in black holes. Or do we search in the center of the galaxy? Do we search on really hot, molten planets with thousands of degrees? And the answer is no. Those are probably crazy places to search because maybe the chemistry of life doesn't work there. So let's go through and let's look at the chemistry of life. And let's see if there's some things that we can conclude about where we should look for life, because the universe is too big to look everywhere. And so if you ask biologists, they might come up with a list of things for where you should search for life. Like they would say, okay, don't search in some place that's too hot, because if it's more than 100 Celsius, then you start to cook things and they can't live anymore. And if it's too cold, well, don't look there. And don't look in an area because if it's too acidic, because if things are too acidic, then it will kill all the life. And the biologist might tell you, don't look in some place that's too salty because the salt will break down the cell walls. And don't look in a place that's too high pressure or has too much radiation or doesn't have the right chemistry. And also you need to be looking for a place that has water. And so this is a list of places that they would say, these are good places for life if you ask a biologist. So let's go through these. This is a picture. Maybe you can't quite tell what this is, but this is an aerial picture taken from the sky of bacteria in the national park in the United States called Yellowstone. And these bacteria are about 95 Celsius, so almost boiling temperature. And you can see on it, this is a pathway here, and you can actually see a park bench and a couple of people walking just for a scale here. So this is maybe 100 meters across. And now this blue and green and yellow stuff there, turns out that's not just pure water. There's actually a lot of bacteria living in that water. Now that water is really hot. It's up to 95 Celsius. And in fact, if we go to the bottom of the ocean, we can find some water, which is over 100 Celsius. And it still has lots of bacteria living in it. And so we thought that these hot temperatures would kill off life. It turns out they actually support life at even these hot temperatures. You might think, how can we have water which is more than 100 Celsius? It's because it's at high pressure at the bottom of the ocean. So let's cross off that requirement for life here. Now, if we're looking at areas which are too cold, let's look at that. We used to think that anything which is too cold couldn't support life. But now, if we go down to Antarctica, this guy, he's drilling in the ice in Antarctica, down at about -20 Celsius. And he's finding life which can live and reproduce and eat and grow down in these really cold areas. So we should cross that off as a requirement. Looking at the acidity of the water. Now this looks like a terrible place. This is a runoff and pollution from a mine in Spain. And it's really acidic, meaning if you tried to drink this water, it would boil your stomach and it would burn you. But it turns out that the red stuff that we see here is actually it's actually a kind of bacteria which loves living in this, what we would think of being poisonous water. Not too salty. Okay, so we can find a really salty area, and it turns out this is in Botswana in Africa. And this is dry now, but sometimes it rains and it gets filled with some of the saltiest salt water that you will ever find. You couldn't support life there. But here's a biologist, and she's out there, and she's walking around, and she's actually found tons of bacteria which love these extreme environments. And so we call all of these things extremophiles. These are bacteria which love extremes, really hot, really cold, really salty, really acidic, stuff like that. And so you can imagine, we can go through the whole rest of the list here, and we can cross all of these things off. Because we can find different kinds of bacteria, different kinds of life, which live in all these extreme environments. What about this last one? Must have liquid water. Turns out that we have never found any kind of life that doesn't require liquid water. And so as far as we can tell, the search for life is basically the search for liquid water. Anywhere where we want to find life, we need to find liquid water. Now, where do we look for liquid water? I mean, liquid water is common throughout the solar system and throughout the universe. Water is. But liquid water is not that common. Water is normally found as a gas, such as in Venus's clouds, or as a solid, like on Pluto's surface. It's not normally found as a liquid. But here's a chart of the periodic table, and you can see it just charts the atom versus how much of it there is in the universe. And the thing that the atom that there's the most of the universe is hydrogen, followed by helium, and then followed by oxygen. So hydrogen and oxygen are the two most common elements in the universe which go into chemistry. And so it's not maybe that much of a surprise that we should find water all over the universe, because hydrogen and oxygen are all over the universe. And so if we want to search for water in the universe or in the solar system, let's search first in the solar system, because that's close. Where should we look? Well, there's a couple of great places to look. First place is Mars. Now this is a picture. This picture is maybe 50 kilometers across, and it's an old black and white picture of Mars. And it's an old picture because it was taken a long time ago by a spacecraft called Viking. And what you can see here is that you see these channels, and these channels look very similar to the channels that we see on Earth, where you have like a river system that then merges into another river system, and it comes out into the ocean, things like that. And so if you go to Mars and you look around, you see all these river channels all over the place. Now, it's strange because you see the river channels, but you don't see the rivers, and that's because all the water on Mars has disappeared. Maybe it froze away, maybe it evaporated. At the time this was taken, we don't know. We think now it's evaporated to space. But what we see is Mars used to be really wet all over. And there's a couple of people who've maybe seen some bacteria on Mars that they think might be like fossilized bacteria, that might be fossilized life. And there's a picture of one right there, this little green thing. And it might be fossilized life. It might be just a rock which looks that way. We don't know yet. So, but what we do know is that Mars is an interesting place. It used to be wet, and so we have some spacecraft, and one's called the Curiosity rover, built by NASA, and it's currently driving around the surface of Mars and doing lots of chemistry experiments and searching for clues to look for what might have what the history of water and any history of life, or history of whether Mars could have had life on its surface is. So that's number one, is Mars. It used to be warm and wet. Number two is a moon going around Saturn called Enceladus. And what's interesting about Enceladus is it has these really big geysers on it. And these geysers, Enceladus doesn't have water on the surface that we see. It's all frozen, made of ice. But these geysers are shooting water out into the space. And how you can't just crush an ice cube and have it turn into a geyser. So instead what's happening is that there's probably a liquid ocean below the surface, kind of like in the North Pole, right? Where you have like ice on the top of the North Pole and below that is the ocean. Well, that's the same thing that's happening here on Enceladus, where you have an ocean below and somehow that water is squirting up through the ice out into space. These plumes come out as liquid droplets, and something on Enceladus must be keeping it warm inside, because Enceladus is a long way away from the sun, so otherwise it's pretty cold there. So we have a spacecraft called Cassini. It just crashed into Saturn about a week ago, and so it's what Cassini was doing was looking for evidence of this water and sampling it when it was up at Enceladus. Now that's Enceladus. This is the third place that we can look is Jupiter's moon Europa. And this photo on the right here, it's about the size of Delhi, you know, about maybe 30 kilometers across. And you can see it has some icebergs in there. And this is a real picture of the surface. And these icebergs look like they're floating around on the surface. And you can see about 6 or 8 different icebergs there. Now, turns out the surface is frozen right now, but recently, in the last maybe million years, these icebergs were floating around on the surface, and that meant there was a liquid surface there, a liquid water ocean, and now it's probably a liquid ocean below the surface, just like the North Pole or Enceladus as well. And so we think that we have liquid water at Europa as well. Now we're working on sending a spacecraft out to Europa to check it out for sure and see everything that's there. But if you have liquid water there, then you might have a lot of interesting possibilities for life. Now, all these things are in the solar system. What about if you want to look for life outside the solar system? I was working on it. It took us, even with the fastest spacecraft we have, it takes us 9 years to get out of Pluto. So it's going to take us 50,000 years to get out to even the closest star. So we can't really send a spacecraft out to the next star. It just takes too long to do that, because which ones of you want to sign up for a spacecraft that's going to take 50,000 years before it makes it to its destination, huh? It's going to be a long time. You can also listen for signals using SETI, which is a search for extraterrestrial intelligence using radio signals, and we're working on that. We can detect these planets around distant stars. Even if we can't go to them and visit them, we can detect them from the Earth. But all these direct searches for life are only possible right now in our solar system. So this is the Mars Curiosity rover. It's one of the most exciting missions that we have out there. It has all these instruments that are driving around on the surface of Mars and looking for evidence of the early history of life on Mars. And so here's a little map of where it's driven. And so every day, the Mars rover, it wakes up and then it drives around the surface. Maybe it moves 100 meters, or maybe it moves 5 meters. It moves to a new rock and moves to a new area on Mars. And you can see in this map here, it's landed in a crater. It used to be really wet in that crater, and now it's dried out, but it's looking for all the past history, what was in that crater. In fact, here's a little map, a little picture of what used to be in that. We used to have this big lake there. In fact, in India, there's an impact crater which was made by an asteroid pretty similar to this. It's in Maharashtra, called the Lonar Lake crater. And lakes are really interesting because, you go to the bottom of a lake and you stick your hand and you pull out this big handful of mud and muck, and it can have a little bit of everything in there because everything can fall into a lake. And so you might think, oh, this just makes your hand really muddy and dirty. But if you study that muck and you study that mud, you can find out a lot about the history of what's happened in that lake, because all of the bugs that have died there and all the fish and all the chemistry and all of the geology turns into that mud, which is the bottom of the lake. So basically what we're doing with this Mars rover is going through and studying the mud at the bottom of that lake. And so we're slowly cruising up and slowly seeing more and more different layers in this lake as we're coming up the side of it. Now, it's not a lake anymore. It's very dry now, but we're going through and seeing its history. Now, the US, of course, is not the only country that's going to Mars. I was so excited to first see the 2,000 rupee note, and it has the Mangalan, the Mars orbiter mission built by Isro, the Indian Space Research Organization. And this is a really exciting mission. Mars is India is one of the few countries which has flown a spacecraft to Mars, and they did it, as you all know, very cheaply. with a great spacecraft that got to Mars on time and efficiently, and is doing some great science there. So this is something that all of India can be proud of. In fact, you know, NASA is so excited for India to have sent this fantastic spacecraft up there. Now, what is the Mars orbiter doing? It's looking for, it's doing two things. The goal is to take pictures of the surface and search for something called methane. And methane is a simple chemical. It's made of carbon and hydrogen. And it's made in two different ways on the Earth. And one is for biology, and that's because if you eat things, then you give off methane. And any, not just people, but any biology here, ants give off methane, and cows give off methane, and people do, and so forth. And so it's given off by a lot of biology. And the other thing that gives off lots of methane on the Earth is volcanoes. Now, we think that Mars is pretty dead, both for life and volcanoes. And what that means is if we go up to Mars and we search for methane and we find methane, then it's got either biology or volcanoes on it. And either of those is really exciting, because either of those is something that we don't know about. And so that's what the Mars orbiter is looking for. Now, the Mars orbiter is just one of many, many missions that have gone to Mars from many countries. In fact, here's a list of them, and it's probably too small for you to read, and that's just because there's too many of them. It's about 50-some missions that have gone to Mars. But all these missions so far have not found any evidence of life. And 50 missions is a lot of missions to send to Mars, 50 spacecraft. So if you look at the history of life on Mars, well, let's look at the history of Earth. And this is just a little timeline that I've drawn. And so the red is the stuff in the past, and the green is the stuff which is today. And if you look at in the past, 4.5 billion years ago, that's when the Earth was formed. And when the Earth first formed, it was too hot to support any life. And that's because it was being hit by lots of asteroids and comets and lots of volcanoes and so forth. And so, so we couldn't, it wasn't a good place to support life when the Earth first started. But then after about 1 billion years, the impacts settled down and we started to have an ocean, and life on the Earth started almost as soon as the oceans formed and the Earth cooled down. And then some of the bacteria made oxygen, and then this oxygen allowed more chemistry to happen, and eventually we made simple animals, and then more complex animals and plants, and today humans. And so humans have come out just in the very last little sliver of life on Earth, the last 1 million years or so. If we look at the history of Mars, well, Mars, I showed you some pictures where Mars used to be wet because it used to have all this oceans and rivers and lakes on it. But right about where this chart shows, this chart shows you blue where it's wet, but then all that water disappeared, and that probably just got lost into space for some reason. And so most of Mars has been dry and dead because it had no water, and we need water to support life, at least to support the we know. And so now we're going to Mars and we're looking for life, and we don't find any life on Mars, probably because Mars has been dry and dead for so long. It's kind of like, I don't know how many of you are really into fossils, and how many of you have tried to look for fossils on the Earth, which are 3.5 billion years old. But it's really, really hard because there's very few places which can preserve a fossil of a bacteria for 3 billion years. And so it's really hard to do that. And so maybe it's not much of a surprise that on Mars, we're looking for life and we haven't found it yet. And so Mars only had this brief window to support life, and maybe it never did, or maybe it just washed away. Maybe it's just hard to find it there because it's hidden. However, on the other hand, if you look at Enceladus, let's look at Enceladus. And Enceladus is warm and wet now, and so is Europa, because it has this ocean there now. And this ocean, well, an ocean is a great place to support life because it's warm and it's wet, and there's lots of chemistry that can happen in the ocean. There's lots of life that can happen in the ocean, and we know that a lot of interesting chemistry happens like at the edge of an ocean on a beach where, lots of interesting things can happen. And so Enceladus and Europa might have lots of areas like this. And so even though we haven't studied Enceladus and Europa up close very much, I think they're probably a fantastic place to go and look for some life. And so let's go to Enceladus, let's go to Europa, and let's find some life there. So that's what I have for you today. Here's just a couple of things to think about. The importance of looking for liquid water. Every form of life that we have is based around liquid water, and so if we want to look for life somewhere else, start looking for liquid water. Maybe life is based on other things, but liquid water is probably a really good thing to look for as well. And there's so many great places inside our solar system to look. Outside our solar system, it's a long, long way away. And so we can use telescopes to study them from the Earth, but it's going to be a long time until we visit them. So that's what I have. Thank you so much.
Thank you, Henry. That was great. We got a whole overview of what we need to do to look for life. And I just wanted to ask you a question myself. What about, what did Cassini provide information about Enceladus that would help answer this question?
Exactly. Can you see me? Am I back to
yeah, you're back.
Video now? Okay.
Right.
So Cassini is the NASA spacecraft which has been at Saturn for about the past 12 years, and it just finally last month crashed into Saturn intentionally, and that's because it was an old spacecraft, and we needed to. It had basically done its job there. Now Cassini is really the one which revolutionized our knowledge of Enceladus, and it showed us that we had from the Earth. Enceladus is tiny, tiny. And so we had no idea that these geysers were happening at Enceladus. And but when we fly up there with Cassini, literally we can see them with the cameras on the telescope, and we can fly through them. And so it's kind of like Cassini is sticking its tongue out and sampling the particles, the ice crystals, which are in space, made by these geysers on Enceladus. And so Enceladus also mapped out the surface. It saw there were some regions which are sort of warm, where they have what we call cryovolcanism. And so cryo means ice, volcanism means volcano. So it's basically ice volcanoes on the surface of Enceladus. It mapped out those. It mapped out some regions where there were cracks on the surface where this ice was coming out of, and so forth. And so Cassini did a great job there. And perhaps we want to go back to Enceladus with a dedicated mission just to study Enceladus, to see what other chemistry and what other interesting things we might be able to find there.
And CB, do you have something for him before I move ahead to students?
Yeah, sure. I just want to share one major thing is that we have grown up reading all those science fiction by Asimov, by Arthur C. Clarke, but we never thought how to find the life, alien life in a very certain and systematic manner, which Henry has just given us that insight, that how to go about it one by one. So it's a beautiful talk by him, and it actually has opened a new venue for me to look for those things.
Thanks. Yeah, it's really neat when the ideas of science fiction are beginning to merge with what we now see in science, and it's so inspiring to see the work that's done by so many countries across the world working together to advance our knowledge.
Yeah.
Thank you.
So I'll go ahead and we have. So just for the two of you, we have at least 36 viewers who show on this, and just remember that many of these viewers are whole classrooms of about 50 students. So we have 32 times 50 viewers right here today. And just so you know, and I'll take some questions. I'll just ask you some questions we have. So we have Sanvi from Rukmini Devi Public School asks, what are the sources of and origin of organic molecules?
Oh, that's a great question. So organic molecules are simple molecules made of things like carbon, hydrogen, oxygen, and nitrogen. And those are, in some sense, the building blocks of life. Now, to make life, you have to do a couple of things. You have to start with the elements, and then you have to make organic molecules from those, and then you have to make amino acids from those, and then you have to make DNA from those, and then you have to make life from the DNA. So it's many, many steps that you have to do to make life like ours. But building the organic molecules is the first step of those, the first or second step, and you have to do that. And there are many different ways to build organic molecules. Sometimes we've actually found that you can build organic molecules if you just put the elements, the simple elements, basically in a jar, and you put lightning through them. It turns out you can also do that if you just kind of heat up the jar and cook it, or if you put electricity through it, or if you shine ultraviolet light on these molecules. They make amino acids pretty easily. And in fact, one of my areas of research is, in fact, how to make these amino acids from simple compounds. And so it looks like that's a pretty easy step to solve. That scientists have spent a lot of time addressing that. And now the question has moved on: how do you make DNA from amino acids? And that's a really, really hard question, and we don't have a lot of insight into that yet.
Yeah, thank you for that. And the next question, we have Archman from St. Thomas School, Dwarka. What about life on the recently discovered 7 planets in the Trappist solar system?
Yeah, so the Trappist system is a really exciting one, and why it's interesting. First of all, it's kind of cool because there's 7 planets, which is very similar to what we have in our solar system. So that's the most we've ever found. But also what's interesting is that some of those planets are in what we call the habitable zone. And what that means is they're not too close to the star that they boil up, and they're not too far away from the star that they just freeze. And they're right in the middle. And so they're in an area where if you put the Earth there, the Earth would be pretty much okay. It's not too hot, it's not too cool. It's the right, in fact, specifically, it's the right temperature for liquid water. And so if you have liquid water there, then maybe you have the chemistry which might support life, and maybe you have life there. Who knows? Now we can't really look for life in the Trappist system because this system is too far away. Even with this fastest spacecraft, you can't get out there. But you can bet that we're doing the best that we can with our telescopes to see what we can see about that. To see, maybe we can measure the temperatures of those planets directly. Maybe we can see if we can see clouds on those planets. Or maybe we can get some clues about their composition, to see if their composition is similar to the Earth's or not, things like that. So that's a really fascinating system that we're going to be spending a lot of time with the next couple of years.
Yeah, and thanks for that. And Hardik Bhasing from Rukmini Devi Public School, Pitampura asks, according to researchers, Sirius, the asteroid, it has a large amount of fresh water than Earth. What are the possibilities of life there?
Yeah, so Sirius is a really it's a huge asteroid. It's almost a planet itself. Right. Sirius is probably frozen because it's a little bit further away from the Earth than a little bit further away from the sun than the Earth is, and so it's probably mostly cold there. And it doesn't have an atmosphere to keep it warm, and it doesn't have the core. The Earth is kept warm by 2 things. The atmosphere, which is the main component, but then it also gets some heat from the core. And because Sirius is smaller, its core doesn't keep it very warm, and the atmosphere doesn't, has mostly dispersed as well, and isn't kept there because there isn't as much gravity. So Sirius is probably too primitive to support a lot of life, or the development of life as we know it. It's probably more dead than we expect. But on the other hand, we could be wrong because there are many places that we would expect to be very primitive, and we find out that they're more complex once we study them into their interiors as well. So we could still be surprised.
Again, thanks. And we have Shivam Gupta who asks, why do we always look for planets which are like Earth? Can't there be creatures which have completely different environments and needs?
Oh, that's a great question. That's a perfect question. Yes, there could totally be life which looks so different than ours. Right. Now, I talked just about water, and maybe life is based on water. And the reason why I think that life in other places might be based on water as well, it's just because water is really common. If you look in the most distant galaxy, if you look in the most distant planets, or the closest galaxy and the closest planets, we basically see water everywhere throughout the whole universe. And so it's very common, and it's a liquid, and that's because Liquid is nice because chemistry happens fastest in liquids. And life is really complex chemistry. Life is the most complex chemistry that we know. And so if we want to support complex chemistry, it's nice to do that in liquids. And the most common liquid is probably water. But we might be wrong. There's other liquids that maybe in other planets are common as well. You know, one of them, for instance, might be hydrogen fluoride. Now, we don't have a lot of hydrogen fluoride on Earth. You only see that in factories and in labs. But perhaps in some other planet, there's something funny going on there, and it makes a lot of this stuff called hydrogen fluoride, and your life there might be based on that instead of water. And it might have a completely different appearance, different chemistry, different thing entirely. So we need to keep our brains open to look for those sorts of possibilities as well. You bet.
Yeah, thanks for that. And Sri Nadasan School from Chennai, you know, we do have visitors from all around India today. And from Chennai, Sri Nadasan School asks, Chandrayaan has found water on the moon, so why not explore moon for life?
Yeah, Chandrayaan, that was one of the real big excitements of the Chandrayaan mission. Chandrayaan was a mission to the moon sent up by Isro. And what was great about that mission also is it wasn't just an Indian mission. Isro invited other countries to participate with it and sent up instruments from England and from the United States and from Romania and from numerous other countries to participate in this mission as an international project. And so that was a fantastic plan of Isro's. And so one of the American missions, one of the American instruments was the one that gave evidence that there was water on the Earth. Now that water is ice water, or not ice water, it's ice, it's frozen. And that's because on the moon, there's no atmosphere to keep it warm. And so in the shadows on the moon, it's very cold. And so this is basically just a frozen glacier of ice on the moon. And so it's not really the best place to look for life because the life that maybe there's some life in Antarctica, of course. But this ice on the moon is much, much colder than anything on Antarctica. And there's no atmosphere to help it out. No oxygen, which enables chemistry. And so maybe this water might support life. Like it might be useful if someone goes to the moon and they're thirsty. They need to, if we have people there, if we have a human base there, we might utilize that water. But for developing life and for having life that can live by itself on the moon, there's better places to look. And that's where we see lots of liquid water like Europa and Enceladus.
Yeah, thanks for that. And we have a question. This is Samir Sachdeva. He's an amateur astronomer. Can space rocks from Mars and asteroids collide with our Earth in the form of meteorites to form life as we have it here today?
Yeah, totally. The answer is yes. And so we've actually found, I showed you one picture on the, it was that picture from Mars where you could see what looked like a little green bug. It was just painted in green. It's not actually green if you look at it through a microscope. They just drew it that way. But that was a rock that came from Mars, and that's because the reason it got to Earth is not that we brought it back with us on the spacecraft, but that Mars was hit by an asteroid. It made a big explosion. Some of those rocks went into space, and then one of those rocks orbited through space for a long time and eventually landed in Antarctica. And in Antarctica in 1984, there was a woman who was driving her snowmobile across the surface of Antarctica, and she came across this rock, and she was a scientist. And she knew, look, if I find a rock in Antarctica and there's no volcanoes around, this rock, where could it come from? It probably came from space. And so she was down there. She was specifically looking for asteroids and for meteors that came from space, and she found this one. Now, it's entirely possible that that life could have formed in two different ways on the Earth. Life could have been created on the Earth, and we don't understand how that, the details of that chemistry, but maybe it happened that life was created on Earth. Or maybe it happened that life was created somewhere else, like on Mars, for instance, or another planet, and then traveled from Mars to land on Earth. And once, if that rock brought some bacteria and brought some bugs, maybe they sort of seeded and created life on Mars. And so that's entirely possible. And so that idea is called panspermia. Spermia meaning seeds, and pan meaning from around the world. And we don't really know whether that is what happened yet or not, but that's an area of a lot of interest of astronomers and biologists.
CB, did you have a comment there?
In fact, when Henry was saying about asteroids and striking together, there's a very interesting fact about one of the Mars meteorites. It fell somewhere in Bihar in late 19th century, and it's called a Shergoti meteorite, which was put under the name of the place where it fell, Shergoti. So that was also a Mars meteorite. And my query is, apart from the asteroids, are comets also playing some part in bringing the life on the Earth as we see it billions of years back?
Yeah, totally. Comets and asteroids could equally contribute. It's harder to find remnants of a comet because when the comet lands somewhere, it just melts and it turns into the ice. So, so usually we talk about asteroids, but comets can have, even that much more chemistry on them, and could be very, very important for bringing that chemistry to someplace else. You bet.
Okay, so we move on to another question. Sherwin from St. John's Public School, Chennai. You were talking about a mission from ESA and NASA. What is the name of the mission?
So these are missions to go to Europa, and one of them, the one from ESA, the European Space Agency, is called JUICE, and JUICE, and that stands for the Jupiter Icy Moons Explorer. And then there's one from NASA, which is called, I think it's called the Europa Clipper, or maybe it's called just the Europa mission. And it's going to be built by NASA, and it will launch in about 2020 or maybe 2025. The European one will probably go up a little bit before that.
Okay. We have a question. Nivedita from Gateway, the Complete School. Why don't the space rocks in the asteroid belt clump to form a new planet?
Oh, yeah, that's a great question. Basically, all these space rocks in the asteroid belt, you would think they should clump to form a new planet because there's lots of rocks there, and they could, except Jupiter gets in the way. And that's because Jupiter is a big planet and has a lot of gravity. And it turns out that Jupiter is a bit of a bully. And if anything starts to form in that region where the asteroid belt is, the gravitational force from Jupiter actually rips it apart and breaks it apart again. If it wasn't for Jupiter, then we would probably have a planet that could form in the asteroid belt.
Yeah, thank you for that. And Vanshika from GD Goenka Public School asks, is there any way we can reduce the toxicity in some of these planets to make them habitable?
In theory, you could do that, but that's a lot of work, and all these planets are very, it's a long away to travel to these planets, and certainly wouldn't want to do is reduce the toxicity so that then we could travel there. So, because right now we have a problem with global climate change on our Earth, and that's because it's becoming slightly toxic here. And that's a really, really small change that we need to do to learn to use less carbon dioxide on the Earth. And so before we start changing other planets and making a change this big on other planets, we need to figure out how to change our planet and stop polluting it essentially, and control it in the proper direction. So that's our first job, not changing someone else's planet.
Yeah, we really need to worry about that. And we in India have Diwali coming up, so that's going to be another big pollutant. Yeah. So Kevin asks, how can a spacecraft cross Jupiter as the gravitational pull is so powerful?
Yeah, great question. So the reason why Jupiter is disturbing all these asteroids in the asteroid belt and not letting them do what they want to do is because it influences them every orbit and it influences, millions and millions of times. If we just have a spacecraft which passes Jupiter, we can actually go by it without Jupiter disturbing our orbit. Or it does disturb our orbit, but we can harness that and do it in the right way. So one of the spacecraft I worked with was called New Horizons, and it actually did what's called a gravitational flyby of Jupiter, or a slingshot. And so we actually used Jupiter's energy to speed up our spacecraft. Our spacecraft is coming like this, and then it went past Jupiter, and Jupiter sped it up a little bit, and then kicked it like that. And so we actually used Jupiter to our advantage, and that's because we knew, it's basically just based on the laws of physics. We knew how many kilograms Jupiter is, and we knew how many kilograms our spacecraft was, and we knew the velocity of each of these things. And then you can just use the laws of physics that Newton has, known about since, the 1600s, and you can plug those in, and you can figure out, if you have this velocity and this mass, what is Jupiter going to do, and what's the spacecraft going to do, and you can figure it out, and you can maneuver it, and you can use the laws of physics to your advantage.
Yeah, thanks for that. Karthik Mehta of Bal Bharati Public School, Gangaram Hospital says, NASA has predicted that there will be a 6th mass extinction, which results in the extinction of the human species. Do you know about anything like that, Henry?
Yeah, I don't think that NASA has actually predicted that. I don't think that's correct. But because it's hard to predict these things. Most mass extinctions have happened due to asteroid impacts. And it's very true that there have been a lot of global asteroid impacts in the past. And so the largest recent one was the what we call the KT impactor. That's because it went between the Cretaceous and the Triassic periods. And that's what killed off the last of the dinosaurs. And that was about 60 million years ago. Now we should be hit by something about every 60 or 100 million years that will be a global extinction. And right now we haven't seen anything coming, but it's entirely possible that we could be hit by an asteroid that would be very large and could hurt life on Earth. And so there's actually a lot of work which is done now by telescopes that are looking for asteroids and seeing if there's any asteroids which maybe in the next 100 years might impact the Earth, and see what we can do about that. Maybe we can redirect them and have them go someplace else rather than hit the Earth.
In fact, I was about to say the same thing which Henry said. When we see it, the law of averages, so this KP extinction thing, which is what we call the mass extinction thing, it happens roughly around 65 million years in interval. So we are right now at the edge of that, because dinosaurs went away in 65 million years ago. So as he said, it may be possible that something happens in next century or something like that, but let's hope it will not.
So I think that's a signal that we should all enjoy life as much as we can, because who knows about when it's going to end. So we have another question from Hardik Bhasin, Rukmini Devi Public School. What are the possibilities of underground life on Europa?
Oh, absolutely. You could totally have underground life in Europa. Europa, if it has energy and it has liquids and it has chemistry, yeah, it could be just like on the Earth, you have underground life. You can go down many, many kilometers below the Earth into some of these like gold mines in South Africa, and you see bacterial life there, and you might have the same thing on Europa. Absolutely.
Okay, so thanks. And Arushi from St. Thomas School, Dwarka says, can humans live on Enceladus or Europa if we find any life there?
Both those are very cold places, and that's because all of the energy in the solar system, almost all of it, comes from the sun. And so you have the sun over here, and then as you get further away from the sun, here you have Mercury and Venus and Earth and Mars and Jupiter and Saturn. And when you get further away from the sun, you get colder and colder. And that's because there's less and less light coming from the sun. And so at the Earth, we have quite a bit of heat coming from the sun. But at Jupiter, you actually have about 25 times less. And at Saturn, you have about 100 times less energy coming from the sun. And so it's very hard for humans to live at those very cold temperatures, even if you dress up warm. I mean, it's very hard. On the other hand, maybe there's something which is keeping Europa and Enceladus warm, because otherwise that liquid water would freeze. And so maybe there is an energy source there that somehow we could utilize. So we need to study those planets more, those moons more, to learn more about them.
And we have another question from Aksha from Gateway, the Complete School. What's the criteria for a planet to be classified as a planet?
Oh yeah, that's a great question. So like some people know about Pluto, and some people call Pluto a planet, and some people don't call Pluto a planet. And at one point there was a vote by a group called the IAU, the International Astronomical Union, in 2006 about whether Pluto was a planet or not. And some of my colleagues went to that meeting. Some people didn't. What they did is they just voted. Vote if you want Pluto to be a planet, and vote here if you don't want Pluto to be a planet. And it turns out there were more people who voted no than who voted yes. But it's an interesting question because no one has really defined what a planet is. And so that's what the IAU was trying to do. The IAU came up with a list of different things. Like, if you want to be a planet, you have to be round, and you have to not get hit by asteroids very frequently, and you have to orbit the sun, and stuff like that. But it's really hard to make this definition because by almost all standards, Pluto is certainly a planet because it has so much geology going on. It's so important to understanding our solar system. And other things like, you look at Saturn. Saturn isn't really round because it's spinning too fast. And so maybe you should call Saturn not a planet. Mercury, people call Mercury a planet, but Mercury is, it doesn't have nearly as much interesting geology happening as on Pluto. And so, things like this. So there's lots of arguments made for different things being planets and not being planets. And so most astronomers still call Pluto a planet. And I still call Pluto a planet, and everybody can still call Pluto a planet if they feel like it. But this is the sort of thing which keeps changing with time. I mean, no one really, as we discover more about the universe, we will discover more about other planets, and we'll discover more what makes up a planet and not a planet.
Yeah, we have a question from Rishit Jain, Balbharati Public School, Pitampura. What kind of signals can we receive from aliens?
Oh yeah, who knows? Maybe Rishit could be one of those people who's looking for them, because we don't know what the aliens are. We don't know, what language they speak. We don't know what kind of radios they've built. We don't know even if they have radios. And so it's a completely unknown question.
And so what is SETI looking for? What kind of signals?
So SETI has made some guesses as to what they might look for, but we really don't know. I mean, they're basically looking for emissions which are a pattern in the radio signal which is not natural.
Right.
For instance, if someone starts sending out a signal which is like a prime number or something like that. That's something which wouldn't happen naturally from a star or from a planet, but would have to have some sort of intelligence to to know what a prime number is and send out a list of prime numbers, something like that. Maybe that's one example, but transmission that we could put together to have pictures which wouldn't be created from, just from nature, something like that. But honestly, anybody's bet is as good as anybody else's. So I bet that many of the students and learners can be the people who would contribute to interpreting those signals and figuring out what's really up there.
CB, do you have anything to say on that?
In fact, he didn't mention that if you read Carl Sagan's Contact, the same thing was there, what he was talking about prime numbers and all, and some sort of a visual thing. When you decode those numbers, then you get something which is decipher by us, and it has to be made by machines, not by a natural source. So it's a long time to go, and Henry is right. I mean, the signal can come in any shape, any form, any sequence. So we don't know yet.
Yeah, that's absolutely true. So we still have a lot of questions, and I'm just going to go ahead and take the last couple. We have Parv from IP Pashchim Vihar. What is the temperature of Europa?
The temperature of Europa, well, it's interesting because on the surface, Europa is frozen. And so maybe the temperature is, you could look this up on Wikipedia, but perhaps it's negative 100 Celsius, something like that. Maybe it's negative 150. But then if you go down below the surface into the ocean, the surface, because it's liquid water, it must be, between 0 and 100, basically. So let's say maybe it's 50 Celsius, something like that. But we don't actually know, and that's because we have not sent a spacecraft there to actually measure the below surface temperature of the ocean. And it'll be hard to measure. In order to directly measure it, you'd have to send a probe down through the ice, drill through the ice until you can put a thermometer down there. But perhaps by a lot of observations and modeling of the geysers and the surface, maybe we can get a good understanding on what's below the surface, even without directly going there too.
So we have, I don't know. So I don't know if we want to open up this avenue, but I want to, we have a question from asking, is there really been any proof for for aliens visiting Earth, like in the Roswell case?
Yeah. So a lot of people ask about that. So,
right.
You have cases. There are some articles you can read about, where there are aliens who landed at Roswell or Area 51 or things like this. And if you look into these, and if you look into them in detail, then behind almost all these, you can find a very simple explanation, like it was an airplane that crashed, or it was a weather balloon, or it was a scientific experiment that wasn't known about. And you can find out that all this evidence, is not actually real. And you might read oh, well, I had a friend, and this friend's mother had a brother who worked there and said oh, it was real and I saw an alien. But then if you look at that, it didn't actually happen that way. And so if you look at it in detail, there's no reputable evidence that we've ever been visited by any sort of aliens. Now, you might think, oh, well, that's because the government is hiding the evidence. And the fact is that many governments like NASA and Isro also are really interested in finding life outside the universe. And that's why we've sent all these missions to Mars and to other places. And so NASA has, NASA spends, hundreds of millions of dollars a year trying to find aliens. That's why we're sending all these missions to Mars. That's why we're sending this mission to Jupiter and to Europa. And that's why we've been operating this mission in Enceladus, is because we're looking for life there. We're looking for aliens. Now, we wouldn't expect to find aliens, maybe, right now with this mission, but it's part of a large process. And so for many decades, NASA has been very dedicated to looking for life throughout the universe. And you can bet that the moment that NASA finds anything, and we found some, this rock on Mars that might have had the fossilized bacteria on it. And sometimes we'll hear, one signal, but we'll only hear it one time and it doesn't come back. Things like that. But whenever we find, the slightest bit of evidence, we're extremely interested in it, and we'd like to write that up and tell people about it. So the moment we find any bigger evidence, you bet that everybody will know about it.
Yeah, that's what keeps the science fiction movies rolling on that theme. So I'll just take one more question. Arpit from Bal Bharati Gangaram School says, what is the Drake equation?
So the Drake equation is just a simple way to come up with an idea of how many different alien species, how many different civilizations there might be in the universe. And so if you think about it, I sort of did a little bit of this right at the beginning when I said how many galaxies are there, how many planets around each star, how many stars in each galaxy, and you can multiply those things all together, and you can come up with the number of planets in the galaxy. And it's like 10 to the 24th, maybe, and or 10 to the 23rd. And then you can say, well, okay, so how many of those planets might have life around them? Like maybe if one planet out of every 10 has life, then you want to put that into your equation as well. And then maybe if, one planet, out of the planets that have life, maybe, 1% of those are life like ours, or is it, 0.1% or whatever. We don't really know what all these numbers are. But the Drake equation is basically just a way of listing all of these different factors and coming up with a guess. It's really just a guess. It's a way to just come up with a guess of how many places in the universe there might be life at.
Yeah, and like you said, that's exactly what you kind of were estimating or showing us in the beginning.
Yeah.
And yeah, so we have a question from Vanshaj of DPS Greater Faridabad. Where do you think would be the most suitable environment for the aliens to exist?
Oh, that's a great question. I think in our solar system, Europa and Enceladus are the best places. Probably Europa, because Europa is a little bit warmer because it's closer to the sun. It has more water there. Enceladus just has water on some small portions of it, and Europa probably has water going over the whole thing. There's a lot of energy, and it's interesting. Jupiter has a really strong magnetic field, and that magnetic field has a lot of radiation, and perhaps that radiation might have a positive benefit. Radiation can hurt people, like taking too many X-rays and so forth. But perhaps radiation in the right place might help promote life and cause life also. So I think that Europa is the best place to go look. Let's go.
So, CB, do you have any comments?
Yeah, just one comment on the Drake equation. It's a very interesting thing. When he calculated that, so on a pessimistic note, it turns out to be that in our own galaxy, we should have 1 million intelligent civilization which can do space travel. And if they send one spacecraft every Earth year for searching other civilizations, so there's a probability that only once in 10,000 years we should have one visit. So it is not that it's happening in your own backyard and suddenly your neighbor says next day that, oh, I saw an alien over there. So it's a very big number, and the universe is so big and we are so small in front of that. So thought of alien life it's all, how much you can think of it, that will be there.
Thank you. Yeah, perfect.
Yeah. And with that, I would like to thank you today, Dr. Henry Throop, for being with us and talking about something so exciting in simple ways that all the students would understand. And it was a great talk, and we have a lot of questions. Hopefully we can put a few more of them on Facebook. But thanks for being with us here today.
Perfect. Thank you for inviting me. Thank you, CB, for being here as well. And thank you to all the students and learners for participating and for your fantastic questions. So thank you so much, and let's keep exploring the universe.
Yeah. And thank you, CB, for being with us here today. And we are all, space is very involved in World Space Week events going on. So even the rest of this week, we'll be going forward and doing more World Space Week celebrations.
Just before you go, one line for these kids. As Carl Sagan has wrote that Earth is our cradle. So once the child has to come out of the cradle and go beyond that. So humanity has to go beyond the Earth to other planets. So that's what these kids would do in coming decades.
Yeah, and exactly. Henry, do you have a line to inspire us?
No, but I think being curious and asking questions like all these students have done is great, because that's what makes the world a better place. Is asking questions and being able to solve them, being able to work with other people in other countries to address these questions, and these are some of the most important questions that we have and that we've always had, and now we're really at a place where we can start to answer them. Like it hasn't been in generations before, we wouldn't have known how to search for life, and now we do. And pretty soon, come back in 10 years or 20 years or 100 years, and we'll probably know the answer to the question, are we alone or not? And I bet we'll find it.
So with that, everybody, thank you for being with us here today. Dr. Throop, Mr. C.B. Devgan, all our students, all our schools, and any friends who have joined us. Thank you for being with us here today, and let's look forward to finding finding life in space. Thank
Yeah.
you, and good morning.
Thank you.